So next, let's look at dry plasma etching. So first, so why we want dry plasma etching? So we know that, so normally we can use wet chemical etching to etch away the materials. So wet etching. For instance, if you want to etch away a silicon dioxide, so the chemical you can use hydrofluoric acid to etch away the silicon dioxide. But the problem for the wet chemical etching is that the etching is usually isotropic. So that means so the etching profile will be something like this. So if you have the wafer to etch and here the mask, so after the etching, wet etching, the profile will be something like this. So we know this is not very good. So what we want very often for the microfabrication is the vertical profile. That means if you here the etching mask, so this etching mask. So after etching, we want the etch profile to be something like this. It's a vertical profile. So when we have the vertical profile, so we can have faithful pattern transfer into the underlying layer. So this means so the feeder size on the top, so the feeder size on the opening is the same as the feeder size on the bottom. This way we can maintain the feeder size. On the contrary, if we do the isotropic etching, it will become something like this. So you see the feature, the opening. So the opening become much bigger than the opening on the mask. So this way, wet etching is not good for the high resolution, but the dry etching is good for the high resolution. And we see there is no undercutting, better process control. So the problem for the dry plasma etching is that first, some gas is toxic and corrosive. For example, we may use a chlorine gas, so we know this gas is very corrosive. There may be some reseparation of the non-volatile compound on the wafers. Thirdly, we need some equipment, clean room equipment, so which costs a lot of money. For example, 200 to 500K for research tools and $1 million for the production tool. So what will happen in the plasma environment? So here we take a CL4 plasma as an example. So there can be a dissociation. So we have electron to hit a neutral gas. It will be dissociated to CF3 and F and plus electron. Ionization. So this free radical neutral can be ionized. A dissociative ionization. So in this case, you have both dissociation and ionization. You create an ion in the end. At last is the reverse process, so which is called a recombination. Recombination, you can see the ions and electrons and the free radicals, they recombine to form the neutral molecule again. In this process, the light will be emitted. So we know that there is the plasma TV. So plasma TV. So for the plasma TV, it is used this process, recombination. So actually, the reaction can be much more complicated than this. For instance, for this gas, there could be more than 50 different kinds of chemical reactions. So now let's look at what gas to use to etch. For example, if you want to etch a polymer, you etch a polymer. So what gas to etch for to etch a polymer? So for the polymer, we know it can be burned away. So normally we can use oxygen gas. We can use oxygen gas to etch away the polymer. Other popular gases are halogens. For example, fluorine, chlorine, bromine, and iodine. So which gas to use depends on whether it will form volatile byproduct or not. For example, for the case of aluminum, if we use fluorine gas, for example, CF4, if we use fluorine gas, so first, there will be chemical reaction, very easily chemical reaction, but the reaction product is fluorine aluminum trifluoride. So this material has a very high boiling temperature, so even though there is chemical reaction, the reaction product will stay on the wafer. Nothing will happen. On the other hand, if we use chlorine gas, Cl2 gas, it will form aluminum chloride. For this one, the boiling temperature is 178 degrees, so it is volatile. So this way, the etching will keep going because the etching product is volatile. It will be pumped away by the pump. So which material to etch? So which gas to etch? Which material depends on whether you form the volatile product or not. Now let's look at other materials. Say if you want to etch away the indium, so we know the indium chloride is hard, but this gas, methane gas, it can form the CH3. So that means you can etch away the indium using the methane gas, using this gas. So you can use the methane gas to etch away indium material. For the case of silicon, so we can use fluorine gas, chlorine gas, or bromine gas. They all have relatively low boiling temperature. For another example is the chrome. So we know that chrome is the material for the photomask. So how to etch away the chrome? So fluorine gas does not work. It does not form any volatile product. So this one, CrO2, this one is volatile, with the boiling temperature is 117 degrees. So that means, so what gas can be used to etch away the chrome? So the answer is chlorine and oxygen. So you need oxygen mixture with chlorine gas. These two gases will etch away a chromium. So this is the overview of the plasma etching mechanism. So first, in the plasma, the reactive neutrals, they are mainly responsible for the chemical reaction because their number is much higher than the number of the ions. So ion can also be reactive. For example, CF3 plus, this is also reactive, but it has a very low concentration, so 10 times lower than these free radicals. So that's why the free radicals will be more important for the chemical etching process. So why the free radicals? We have more free radicals than ions, is because first, the neutrals are generated at a lower threshold energy. For instance, maybe less than 8 electron volt. For comparison, the argon is ionized at 15.7 electron volt. So that means it's more difficult to form ions than forming the free radical neutrals. Secondly, because those free radicals, they are not charged, they are neutral, so they have longer lifetime in the plasma. So on the other hand, because the free radicals, they are neutral, it will come to the surface by diffusion process, so they are not directional. On the contrary, we know the ion will be accelerated to bombard the surface. So that means ion, even though it does not help the etching too much, it can contribute to the isotropic etching process. So now let's look at free radicals, chemical etching, and ion physical etching separately. So for the chemical etching, normally it has very selective but isotropic. So very selective means the etching rate of different materials is very different. For example, if we use oxygen gas, it can etch away the polymer very fast, but it will not etch silicon or metals. That means the etching rate will be very different between the metal or silicon and the polymer. So this is called highly selective, high selectivity. So the etching rate is also fast, but the etching is isotropic. So that means etching something like this. So you may wonder how come you can etch the material below the mask? If the free radicals come to like this, it still cannot etch below the mask. So this is because the free radicals, they have very low snaking coefficient. It's called snaking coefficient. So that means, for example, 0.01, that is 1%. So that means we have this fluorine. So when this fluorine comes to the surface, nothing will happen. It will be bounced back, again, come back here. Then there is the chemical reaction. So only 1% of the 1%, there will be 1% possibility there will be chemical reaction on the surface it hit. This gives the isotropic etching process. So here is the example of the etching of silicon using SF6, this plasma, SF6 plasma. So this one, as we said, the etching is isotropic. So the higher the power, the more the flow, the higher the etching rate. So in this example, it gave about 1.6 micrometer etching rate, then get stabilized. So for the modern etching machine, it can go really fast. For example, it can go to 50. It can etch 50, so 50 micrometer per minute. It's very, very fast. So now let's look at a physical etch. So this is the ion. It is effectively ion bombardment. So why the wafer will be bombarded? So this, as we know in the previous chapter, in the previous part, so we know that so in the plasma environment we have the voltage drop along both electrodes. If you remember, so we have this curve, right? So here is the anode, here is the cathode. So we have the voltage drop. You can see, so the bulk of the plasma is positively charged, and we have voltage drop on this electrode. We have also voltage drop on other electrode. But this voltage drop is because electron gets lost very fast, and also because we apply sometimes for the DC plasma we apply a voltage. But here it is not DC; it is RF plasma. So for the RF plasma, there is no DC voltage. But because of the property of the plasma is positively charged, so there will be voltage drop along both electrodes. So this voltage drop will accelerate the ions to bombard the surface. So this gives the physical etching of the material. So obviously, this etching is very directional and but the etching rate is slower because of the lower concentration of ions compared to the free radicals. There can be many different kinds of ions. For example, chlorine ion, Cl4, Cl3, Cl2, argon ion. If we use argon plasma. So there is in the plasma environment there is also negative ions. For example, C something maybe like this, Cf3 minus. So do you think those negative ions will contribute to the etching or not? So do you know whether those negative ions will contribute to the etching or not? Actually, it will not, because the negative ion will not hit the surface. You see the barriers. So this is positively charged. So negative ion will be kept into the bulk of the plasma. So only the positive ion gets accelerated to bombard the sample surface. So now we have seen the etching by the chemical etching and the physical etching. So the chemical etching is done by the free radicals. The problem for the chemical etching is that it is isotropic. So it is isotropic. For the physical etching, we know it is anisotropic. You have the directional bombardment. So now we want to have those things come together. This is called ion enhanced etching. It's also called chemical etch assisted by the physical bombardment. So how will the ion help the chemical etching? There can be a few things to happen. So first, the ion can help surface absorption, can help an etching reaction. This by physically damaging the chemical bond of the material. For example, if this is the silicon, so we have ion bombardment. When you have the ion bombardment, so the bottom part will be damaged. The lattice will be damaged. So when they are damaged, the etching will be faster. It can also help to remove the byproduct. So we know that for the etching, we can use, for example, we use CHF3 gas to etch silicon dioxide. So this gas, it will form a fluorocarbon polymer, something like this. So you have the carbon, they are fluorine here. So this is the fluorocarbon polymer. So this polymer will be coated on the side wall as well as on the bottom of the wafer, at the bottom of the pattern. So the fluorocarbon polymer on the bottom will be removed by the bombardment, but the fluorocarbon on the side wall will be less removed. So this way, it can give you anisotropic etching. It can also help to remove the unreacted agent. So this is the first example of the ion-enhanced etching mechanism. So in this case, we have two gases. First one is the xenon difluoride. So this one is there is no plasma. There is no plasma. It's just this gas. So we know that this is noble gas, the fluorine gas. They are not. This compound is not very stable. So it will generate a fluorine. On the silicon surface, it will generate fluorine. So this fluorine will react with silicon to form a silicon tetrafluoride. But the action rate in this case is not very fast. It's only half nanometer per minute. The same is true for argon ion bombardment. So we have the argon ion bombardment, the action rate is also slow. But we have the argon ion bombardment plus the xenon difluoride gas. You see the action rate is much faster. So this is because the argon ion will damage the silicon lattice. So when the silicon lattice gets damaged, the action rate will be much higher. So because this is a very important concept, so here I want to summarize the process. So first, ion does not contribute much to the etching process because it's very low acidity, 10 times lower than the acidity of the free radicals. So the neutral radicals is also called free radicals. It is also called. So the free radicals actually contribute mostly to the chemical reaction. As a result, so even though there is the chemical direction of bombardment, the overall etching can still be very isotropic. As we have seen, SF6 etching of silicon is very isotropic. But how to achieve anisotropy? So there are two mechanisms by the ion. So first, it's called energy-driven anisotropy. So in this case, the ion will damage the substrate. This way, the action will proceed faster along the vertical direction, slower along the horizontal direction. In the second mechanism, it is called inhibitor-driven anisotropy. So here, we have the polymer or other passivation layer on the side and also on the bottom. We have polymer on the side or on the bottom. But the inhibitor layer on the bottom will be removed by the ion, so leave behind the polymer protection layer on the side wall. So this way, we can have anisotropic etching. So here are some plasma etching systems. The first one is called a Pyro Etcher. This way you can put many wafers side by side, and you have the plasma, something called a plasma shield. So the ion will be shielded. There is no ion. It is the pure chemical etching. So pure chemical etching, no ion bombardment, because the ion is shielded by this plasma shield. So the etching, because when you put the wafer this way, you can imagine the etching rate will not be uniform. This is not used for the critical etching. It's only for example, to remove the photoresist residue. You just want to remove the material residue. You don't care about the etching rate. Then you can use the Pyro Etcher. So to remove the photoresist, so we use oxygen plasma. So this one is chemical etching, very selective, but it is not anisotropic. It is isotropic etching. The second one is called a parallel plate etcher. So here we have the top plate and bottom plate. So you can see the configuration is similar to the spatter separation, but there is one very important difference. For the spatter separation, so the target is on the small electrode, but for the etching process, so the wafer is on the smaller electrode. So the area of this electrode is much smaller than the area of this electrode. So actually, as you can see, this electrode is connected to the ground. So we know that this way there will be no bombardment, so very little bombardment on the top, a lot more bombardment on the wafer. So this way you etch away the wafer rather than etching away the top electrode. So we have known this process when we in the previous part for the spatter deposition process. For the spatter deposition, we know that the voltage drop V1 divided by V2 is proportional to A2, A1. So you see the bigger electrode area, the smaller voltage drop. So here, but the RE profile for this process, it is a low density plasma, So as you can see, so the neutral species, this is the gas molecule. For example, CF4 gas is 10 to the power 15. But the reactive neutral species is 10 to the power 12. The ions and electron is only 10 to the power 8 or 10 to the power 12. So very low plasma density. So this is not very good. So this is the RE summary. So because the RE can achieve both isotropy and selectivity as well as high etching rate, it is very heavily used. It works for most semiconductors and dielectrics. So previously we have seen the etching of silicon. For the silicon etching, we can use SF6 gas, or CF4 gas, or CHF3 gas. So we can use those gases. To etch silicon. So we can use similar gas to etch silicon dioxide. So silicon oxide can also be etched by those gases. The same thing is true for the silicon nitride. They can all be etched easily. But for the metals, for how to etch with the metals, so most metal cannot be etched, but some metal can be etched. For example, we can use chlorine gas or BCl3. So we can use those gases to etch with aluminum and also titanium, as well as fluorine gas for the titanium and tungsten. So for the chrome, so we have seen that we can use the mixture of chlorine gas and oxygen gas to etch with the chrome. But many other metals will be very difficult to etch. For example, nickel. Nickel is very difficult to etch. The same is true for the gold. The gold is also difficult to etch in the plasma. We can etch it in the plasma, but it's mainly ion bombardment. There's not much chemical reaction in it. So because the regular RE process is a low density plasma, so the etching is not very efficient. So the solution is to have high density plasma. High density plasma is called HDP, high density plasma. So we know that for the regular RE, the ion flux and ion energy is coupled. So we have higher power, you have more ions to bombard the surface, and you have higher energy of the ions. But for the HDP system, so the ion flux and ion bombardment energy can be controlled independently. And for the HDP, so we have higher ion density. So the ion density is similar to the electron density. So because ionization is much more efficient, so we can work at a low pressure. So when we have lower pressure, there will be less collision, more directional etching. And also the ion energy can be controlled. For example, sometimes we want low ion energy. So when we have a low ion energy, the damage to the substrate will be smaller, and also the selectivity will be higher. Etching rate selectivity. Selectivity is also higher. So when we have a lower ion energy, the physical bombardment is less, so chemical reaction more. So we know that for the chemical reaction, you can have very selective etching. That means the etching rate of different materials can be very, very different. For example, if we want to etch the silicon using SF6 gas, and the mask can be resist. So when we use the resist as the etching mask to etch silicon using SF6 gas, so the selectivity can be 1 to 100. Can be very high if we use a low power. So here is that there are two types of the HDP, high density plasma system. The first one is called ECR, electron cyclotron resonance. The second one is called ICP, inductively coupled plasma. So at present, ICP is much more popular than ECR. So at the University of Waterloo, so we have maybe 5 or 6 ICP etching systems, but that way we don't have any ECR etcher. I know that at McMaster University, so they have the ECR etcher. So this is used in the 1985. It's developed in the 1985. So here is the comparison between the regular RIE process and high density plasma etcher. So first, for the high density plasma etching, as we have seen, because the ionization is very efficient, so we can have lower pressure. But for the RIE, we need, but not necessarily 50, so 10. So 10 milliliter may be okay, but not much lower than 10 milliliter. But for the HDP, we can go to even half a milliliter. So the plasma density, you can see is 1 to 2 orders higher plasma density for HDP etcher. So the ion energy, so we can have lower ion energy by using lower baggage power. This bottom electrode, so we have bottom electrode. Top one is ICP high density plasma. For the bottom one is regular CCP, capacitively coupled plasma, parallel plate plasma. So this one controls the ion energy. This one controls the ion number. So the ion energy can be much smaller. We have lower ion energy, as we have seen. We have higher selectivity and lower damage to the substrate. But for the regular RIE process, the ion energy has to be usually much higher. So the ion current, so high density plasma has higher ion current, a little bit higher electron temperature. Ionization rate is also higher for the high HDP plasma. So now let's look at the ECR and ICP, electron cyclotron resonance plasma and ICP inductively coupled plasma separately. So first, they both use magnetic field. The difference for the ECR, so we have the DC, we have the DC magnetic field. But for the ICP, so we have the coil. So when we have the coil, so we have AC magnetic field. So that means, so we have this term. So the magnetic field change with the time. So for the ICP, so when we have the magnetic field change with the time, we know this will generate and this will generate electrical field because of the we know about Maxwell equation. So E field. So when we have the changing magnetic field, so we can generate electrical field. So this electrical field, so electron will move in a circular fashion, and the electrical field is also circular. This way, electron will gain energy by this electrical field. So for the case of the electron cyclotron resonance plasma, so we have the DC magnetic field. So the electron will go in a circular way. If the movement of the circular movement has the same frequency as the microwave supply frequency, which is typically 2.45 gigahertz, then there will be resonance. That's why it's called electron cyclotron resonance. So when there is the resonance, the electron move in a circular way, and it will gain energy from the microwave. This way, electron will gain the maximum speed, and it will create more plasma. So this is the schematic of the ICP etcher, inductively coupled plasma etcher. So you can see, so first, so we have the coil. This coil can be 3 turns. So this coil can be the 3D coil. Okay, so last time we got some problem. So I will continue with this slide. This is the ICP etcher. First, so we have the coil. So normally there are 3 turns. There are 3 turns of the coil. So the coil can also be the planar. So planar means you have the coil something like this. You can also have this kind of coil at the top electrode. Then there is the baggage power. So this is the baggage power. This gives you how many what's the energy for the ion to bombard. How many electron volts of the ion to bombard the sample surface. So this determines the physical bombardment, and this one determines the number of the ions. So here you can see this is the bottom electrode. You don't see the top electrode. Actually, the entire thing will be considered as the top electrode for this parallel plate. The bottom one is the parallel plate, the bottom one. So this is the last slide. So you can see this is the etching of different materials. So for the casing of the silicon, so we use the fluorine gas or chlorine gas or bromine gas. I think at the moment for the production environment, people use the HBr. This is the gas used. But for the research, so in our university, we don't have this gas. So we have chlorine gas and we have a fluorine gas. To etch with the silicon dioxide, so we use similar gas to etch with the silicon dioxide, so fluorine gas, but not chlorine or bromine gas. So silicon nitride, also different kind of fluorine gases. For aluminum, we need to use chlorine gas because the aluminum fluoride, so we know that aluminum fluoride, so this material. So aluminum fluoride is not volatile, so the fluorine gas will not etch with the aluminum, but chlorine gas can do it. So tungsten, we can use fluorine gas and the chlorine gas, titanium, chlorine, fluorine, titanium nitride, titanium silicon, photoresist. So we can use oxygen to etch with the photoresist. So actually, if we use fluorine gas, it can also etch with the photoresist. But when you use fluorine gas, then the etching selectivity between the resist and the silicon will be low. But when you use oxygen, we know the selectivity can be very high. So you etch with the resist without etching away the silicon below. Now this is the normal etching process. So if you want to know more about etching process, so you can go to my slide on my homepage. So there you can see a very important etching process, which is called deep RE. The deep reactive ion etching. So in our campus, there is one deep RE in the quantum nanofab, another deep RE in the surf lab, the MAPS lab. So for the deep RE, they use something called the Bosch process. This process. They use the Bosch process. The etching rate can be very fast, can go to 50 micrometer per minute, and the etching side wall is also very vertical, and the selectivity to the mask, resist the mask or oxide mask is also very high. That's why it is very widely used for the MEMS. For example, the microphone in your cell phone, the lots of the accelerator meter in the car, all those things they use the Bosch they use this deep RE, the Bosch process to fabricate bulk silicon devices. Okay, thank you.